Okay, so we can simplify to these two forms. By simplifying, we get these two poles. Fine. Now we can write our transfer function in this form. Accordingly, we can rewrite our transfer function in this form. So it becomes obvious that if we take the inverse of Laplace transform, we get the expression for yt, and it depends strongly on zeta. P1, P2, they are depending on zeta. So we can say that yt, that strongly depends on damping factor zeta. Now there are three different cases, you know. In one case, zeta is greater than 1. Now, if you substitute here, zeta is greater than 1 in these two poles. If you consider zeta is greater than 1 in these two poles, P1 and P2, we will have two distinct real poles. You see? If you consider zeta greater than 1 in these two poles, P1 and P2, it becomes obvious that we have two distinct real poles. And this class of systems is called overdamped system. This type of system is called overdamped system. Can you tell me, if we consider zeta equal to 1, what happens? How many poles are there?
Sir, equal.
Equal. Real or what?
Real and equal.
Yes. What's your roll number?
Sir, 19CH30036.
You see, if we consider zeta equal to 1, we get two equal poles. And that is minus 1 by tau. Okay. So this type of system is called critically damped system. This is the critical value, zeta equal to 1. What happens if we consider zeta less than 1? Anyone?
So we get two complex conjugate poles.
Yeah. What's your number?
19CH10007.
Yes. You see the poles look like this. Agree? If we consider zeta less than 1, in fact, in between 0 and 1 we are considering, we get two complex conjugate poles. And the corresponding system is underdamped system. And the poles are as written, you see, P1 and P2. So why we have considered the lower limit for zeta 0, in fact greater than 0? Zeta is considered in case 3 in between 0 and 1. Why? Why not 0 or less than 0?
So zeta is damping factor and cannot be negative. That's
No, if it is negative, what happens? We have discussed this issue as well.
yes, sir. If zeta is negative, then it is unstable system.
Yes.
Oscillation with increasing amplitude.
Yes. Yeah. So we are considering basically the stable systems. But definitely there are certain unstable systems we are also dealing with controller. Okay. Now let us consider, we want to find now the dynamic response. So dynamic response means we need to consider some change in the input variable, and then we need to take the inverse of Laplace transform. This I indicated before. Transfer function is given to us or known to us. We need to consider certain change in the input variable, and against that change we want to find y in time domain by taking the inverse of Laplace transform to investigate the dynamics. That is what we are going to do. Here we are considering, you see, step input with magnitude A. So AS we are considering, sorry, FS we are considering as E by S. Okay. Now in place of F bar S, we are simply substituting A by S. So the expression of Y bar S looks like this. Expression for Y bar S looks like this. Now we will we'll take the inverse of Laplace transform, and we will get the expression for Yt, a different expression actually for 3 different cases, and they are directly given to you. I repeat, if we take the inverse of Laplace transform, then for the overdamped system, I mean zeta greater than 1, we get this expression for Yt. We get this expression for Yt. Okay. Now if you consider the next case, that is a critically damped system, then we get this expression. If we consider the critically damped system zeta equal to 1, then we get this type of response. Now let us come to the third case. This is the expression for y in time domain. So you know I have given the final expressions to you for 3 different cases, but at least you have to do the derivation for one case. I repeat, I have given directly the final expressions for 3 different cases for yt. You need to derive the expression for y at least for one case. Then you can understand it, the derivation. Okay. Now for the underdamped system, it has another expression that is shown, you see, through the second equation, this one. This is the second equation for yt. Second equation in the sense we just rearrange this first equation and we get this. For the underdamped system, now here we have 2 new terms appear. One is omega, another one is phi. So those 2 terms also given. In the second equation for underdamped case, there are 2 new terms. One is omega, another one is phi. And let us define these 2 terms. Omega is here radian frequency. And phi is the phase angle. Okay, so these are the three expressions for three different cases, and we will discuss different issues from these three equations. Mathematical details will be, mathematically we'll analyze these three equations and find many features. Okay, so let us come to the next issue. We want to gain some experience through the graphical representation. We want to have certain explanation from this graphical representation. You just draw it. This is our input function f, and initially it is at steady state. That's why this horizontal line with the value 0. Then we are introducing a unit, a step change having magnitude a. Fine. Basically, we want to have some graphical representation of this, how the response we have with varying the zeta value, that we want to see. So for this, we are introducing a step change in input variable f with magnitude a. So in Laplace domain, this is basically a by s. Okay. Now let us come to this representation, graphical representation. So as we consider for first order system in dimensionless form, similarly we are following here or producing the plot with y divided by akp versus t by tau. As we followed for first order system, we are similarly producing this plot between y divided by akp and t by tau. Both are dimensionless quantities. So you see this is the initial value, steady state condition, and then we are introducing step change with magnitude a in f. That's why you see initially it was here at 0. But because of that step change, it is just going up to 1. Okay. Like this input variable, 0 value at steady state. Similarly, y by akp was also here, one horizontal line. Because of this step change, this is also going up and reaching 1 value. And then this is the actual response in terms of y by akp. So red color indicates, or red color corresponds to the lowest zeta value, 0.1. Then green color for zeta equal to 0.5, higher than the previous value. This blue color represents zeta equal to 1, and this black color zeta equal to 2. I think this is also indicated before. Zeta small means small damping. Oscillation is large. That is quite indicated here. That is also quite obvious here. Zeta is small means more oscillation. Zeta more means less oscillation. This is a plot for two dimensionless quantities. One is y by AKP. Another one is t by tau. Again, step change in input variable with magnitude capital A. It is obvious that if as zeta decreases, oscillation increases. Okay. And this final value theorem we can apply to find the ultimate value of the response. The same thing I told before for first order system as well. If you want to find the ultimate value of this y by AKP, that is here you see we got 1. For that we need to consider or we need to apply the final value theorem. That is limit t tends to infinity yt by AKP. Okay. And if you apply in terms of Laplace domain, then it should be s tends to 0. S y bar s. Fine. Now our next topic is underdamped system time domain features. Our next title is underdamped system, and we want to study some time domain features. See, this is typically seen that when the first order systems are connected in series, we get overdamped response. If we connect the first order systems in series, and if we find the yt, that is basically the overdamped response. And if we go for system plus controller, then usually we get underdamped response. Okay. The first case corresponds to overdamped response, and that is if first order systems are connected in series. And second case, if we employ a controller with a system, the resulting response is underdamped response. But one thing I want to mention here, sometimes for the second case, system plus controller, we can have this overdamped response. Okay, so it depends on basically the controller and particularly its tuning parameters. I repeat, for the second case, I mean system plus controller, we also have overdamped response, and it mainly depends on this controller, particularly the controller tuning parameter values. And we will discuss this issue also. Now you see, first we want to cover this second case, underdamped response, because the name of this course is process control, no? So we want to first discuss the system with controller. But definitely we'll also discuss this overdamped response after that. Okay, first let us go to discuss this underdamped response because controller is involved here and we are currently discussing the process control part, but definitely we'll discuss this overdamped response as well. So this is the graphical representation, for a underdamped system. This is the graphical representation for underdamped system. You just draw it. Drawn this carefully. So this is for underdamped system response. Okay, here we are considering a equal to 1 I have mentioned. And this is only time. Okay. And here you see this T suffix R. This is called rise time. Here is called rise time. These are the nomenclatures we are using here. T suffix R is called rise time. T suffix P is the peak time or time to first peak. T suffix S is the settling time. And capital T is basically the period. Fine. Now the settling time TS, I have written here plus minus 5%, but it depends on you. You can also consider here plus minus 1%. That means you have to wait for a little more time. Maybe plus minus 2%, plus minus 4%, plus minus 5%. It depends on you. Where you want to basically settle or which value you want to consider as settling time. Okay. And here you see it is shown that plus minus 5%. That means for this peak and for this peak, two consecutive peaks, The change is almost, same. This is one peak where we have plus 5%. This is the next peak where we have minus 5%. I mean, they are very close. It may not be exactly 5%, but they are very close. So sometimes it is considered plus 2% also. Okay. Now, can you tell me what is the value or expression for TP in terms of capital T? Anyone? What is the expression for peak time in terms of capital T? Anyone can give the answer?
Value of Kp at time equal t equals t by 2, capital T by 2.
Yes, this is TP you are saying.
Yeah.
Yeah, what's your roll number?
19CH 10051.
10051, yes.
Yes.
So he is saying that TP, peak time, is capital T by 2. Now, what is the expression for TR in terms of capital T? What is the expression or value for TR in terms of capital T?
Sir, T by 4.
Yes. What's your roll number?
Sir, 19CH 10009.
It is capital T by 4. But do you think we will have exactly T by 2, T by 4? What do you think?
No, sir, it's the approximate value. The exact
Yes.
value is something else.
How we can determine the exact value? Any clue? So these are approximate value. Okay. So we want to know, along with the approximate value, the exact value. Question is how we can determine those exact values for ice time and peak time.
Sir, if we consider a sine wave, then, or like trigonometric function.
So why we have discussed then so many equations before coming to this graphical representation? I have given 3 equations for you.
I mean, I think so. Like we consider any like
Sir, we can
sine
take the
wave or cos wave.
derivative and equate it to 0. So we can find the maximum.
Then we can get which value?
Exact value of TP we can find.
Yeah. For which expression you were saying?
So for the expression for y by Kp.
This one?
Yes, sir.
Yes.
No, so yeah, it's underdamped. Yes, so this one.
Yes, this is underdamped. What's your roll number?
So 30036.
Correct. Now, what expressions or values your friends told? Those are the approximate values, but they are not the exact values. If we want to find the exact values for TR, TP, and many other, terms, we need to consider the expression which we have determined before. Now, let us come to those expression. Okay. Let us start with this peak time. We want to find the exact expression for all these terms: peak time or time to first peak, rise time, settling time, etc. Now let us start from this peak time. So this statement, or you can say the definition, it is quite obvious. This is the time required for the output to reach its first maximum value. And we got the answer from you, Tp equal to capital T by 2. Capital T by 2 means this one. And how we get this one? You see the right hand side. Omega is, if you recall, basically the radian frequency, radian per unit time, and T is the period. So if we multiply, we get 2 pi. Okay. So T equal to 2 pi by omega. And omega is basically root over of 1 minus zeta square by tau. This also we have written. Clear? Now you go to find the exact value. And for this, you consider this dy dt y divided by kpa equal to 0. And let me know the expression for t, small t. That is nothing but Tp. I repeat, this is the approximate value, capital T by 2. Now we want to find the exact value. And for that, we can consider this time differential equal to 0. And considering this, we will get the expression for small t. That small t is basically Tp. You find the expression. Okay, I am taking a 5 minutes break, and after that I will ask this, what you get. Fine, you consider this time differential equal to 0 for the expression of underdamped system, and find the expression for small t, that is nothing but t suffix p. Let me know the answer after 5 minutes. I am taking 5 minutes break. Yeah, anyone got the expression for TP?
Sir, I got it as tan inverse of omega tau by zeta minus phi by omega.
So that would be equal to 0.
Anyone else? Any other expression?
Yes, sir. I got tan inverse of omega tau by zeta minus phi whole divided by omega.
Even that would be 0. It's the same issue, I think.
Anyone got the same value? Capital T by tau? T2?
Yes, sir.
So, I think what's happening here is that these solutions that were given, they're finding out that t is equals to 0, because I think that the derivative at t equals to 0 is also 0. So we need to have a higher solution than that. So that will be the same solution, the exact solution that is written here, 2 pi by omega.
See, you got something like one all the coefficients or parameters within a single term multiplied by sine omega t. Got this expression or not? I repeat, dy dt equal to, there are many coefficients or parameters multiplied by sine omega t. You got this or not?
So sine omega t plus phi.
Sir, so after simplifying, I'm getting tan omega t plus phi equal to tan phi. And the first solution is TP. So like the first value of t for which this satisfies is TP. So omega should be pi. Omega t should be pi.
So I think you have started with second expression for yt, no?
Yes, sir, the second expression.
You substitute the
Sine omega t plus phi expression.
okay. So I did with the first expression. Basically something multiplied by sine omega t equal to 0. Something includes the different parameters, so that should not be 0. So sine omega t equal to 0. That means sine n pi.
Yes, sir. Then since it's the first solution, n will be 1.
So n equal to 1. And then t equal to, you will get the same expression, capital T by 2. See, I do not have the derivation to show you. You have to do it. Okay. I do not have the derivation to show you. So you have to do it. And as I told the answer, it will be exactly capital T by 2. Even if you consider this derivative equal to 0. If anyone got, let me know. Or anyone can get it with certain clue, let me know. I think without doing this, it's difficult to proceed for the next derivation.
Hello, sir.
Yes.
So am I audible?
Yeah.
Yes, sir. I got t equal to pi by omega. If that is what you're asking.
Yes.
So like I took the derivative of the second equation, the modified equation where we have omega and pi.
Mm.
And based on that, I got the last equation as tan omega t plus phi is equal to tan phi.
Mm.
So from there we can get omega t equal to pi per solution for TP.
Yes, sir. Yes, sir.
Getting?
Yes.
Anyone else? I had 2 students got.
Sir, I also got the same solution.
Capital T by 2.
Yes, sir.
Okay, good. Anyone else? See, you who did not get, you try to get it. I'm going to ask you. You first try to find the peak time. I'm going to ask you, so you derive the expression for Tp, considering this time derivative equal to 0. And who completed this, you can go to this part. Overshoot. That we are expressing by capital A by B equal to this expression. You first see the plot to understand this, the definition of overshoot. So if you revisit the plot, I hope you can give the answer that how we can determine capital A. I repeat my question, you first revisit the plot y divided by Kp versus T for the underdamped system. Now let me know how we can determine capital A. Anyone can give the answer?
So we'll put T equal to Tp.
Yes.
A minus 1 by, so A by B.
And B, you know?
Yes, so B is 1.
B is the ultimate value of the response, that is 1. If you consider, if you apply the final value theorem, you can get it. So if you know how to determine A by B, let me tell again to everyone. Capital A we can determine by considering y divided by AKP at T equal to Tp. That is A. A is the maximum value of y divided by AKP. And that is the corresponding value of T equal to Tp. Corresponding value of y AKP at T equal to Tp. So you determine capital A first. Just you substitute in place of T, Tp and get A. And B you know that is 1. By this way you calculate overshoot A by P. Let me know first what is the expression for A and what is the expression for B and final expression. Go ahead. Anyone else got the expression for Tp? One 10060. Soeb Nazir. 10061. Tridipta Das.
Yes, sir.
Got the expression for Tp?
Sir, I got sine omega t is equal to 0.
Which omega t? Sine omega t.
Yes.
Equal to 0 you got.
Yeah.
So that is equal to sine n pi. You write?
Yes, sir.
So here n equal to 1.
Yes, sir.
So I think you are getting omega t equal to pi.
Yes, sir.
So t equal to pi by omega.
Okay.
And that is basically capital T by 2. Agree?
Yes, sir.
Okay. 10062. Now, Tridipta, you go to the next question. Find overshoot.
Yes.
10062 63 Udaya Misra 64 Utkarsh Singh 65 66 Chinmoy Jain 67 Ronak Agarwal 68 Sivoy Dixit 69 70 Ayush 71 Shikha Kumari 72 Ayush 73 Aditya 75 Mohammed 76 Akhil 77 Rosni Kar 78 Yash Jain 30001 Abhishek Kumar.
Yes, sir.
Got this?
Yes, sir. Sin n pi. Sin omega t equals to 0 and turning it to n pi. I got the that TP part. And I am calculating overshoot.
Great. Carry on. 30002 Achal Kumar.
Yes, sir.
Three-
Yes.
Yeah. What is your status? If you are not
Will-
getting, you tell me so that I can help you. What is your status?
Yeah. Wait. Let me connect my earphone. Omega, pi omega.
Pi omega?
Wait, let me calculate. TP equal to T upon 2. T upon 2, I guess. That will be the.
So what you
Hello,
got
sir.
for in terms of trigonometric function? Did you get any trigonometric function? And
I
that is
didn't
equal.
make trigonometric. I just equated it to 0. Like the answer will be T upon 2.
Oh, I
Pi
got.
tau upon 1 minus.
I got. So you have
TP, that
considered
TP.
T. You substituted T by 2 in the main equation.
Yeah.
Okay. Back calculation you were doing that. Okay, fine, no problem.
Thanks.
You try later, I think, to get this equation. Okay.
Okay, sir.
30004 30008 9 10 11 30012 13 14 15.
Yes, sir.
What is your status, Rohit?
I differentiated the rearranged expression and got tan inverse of omega tau by psi minus phi is equal to n pi.
So it is not getting converged to the right answer, no? Okay, you try, no
And
problem.
I am not sure that n should be 0 or 1 or minus anything.
Yeah, you try again. Okay. What I told, if you start with the first expression, what I did, something multiplied by sine omega t you will get.
Yes, sir.
And something is not equal to 0 because those are multiplication of all the parameters. So sine omega t equal to 0 basically. That is equal to, again, 0 means sine pi, sine n pi.
Yes.
From there you try to extract the answer. Okay, fine. Anyone got the expression for overshoot?
Yes, sir.
You got?
Yes, sir.
So what is basically a plus b you got? If you substitute t equal to tau tp, you will get a plus b, no?
Yes, sir. That is 1 minus e power minus pi zeta by 1 under root 1 minus zeta square.
1 minus or 1 plus?
So 1 minus a plus b, where b is 1.
No, it should be 1 plus. Because a plus b you are finding, no?
Sir, a plus b will be 1 minus because once we convert sine of pi plus sine of pi plus 5 in the equation, the negative cancels out.
So what you were saying, 1 minus exponential of?
1 minus exponential of minus pi zeta by under root 1 minus zeta square.
No, it should be 1 plus. You check.
Yes, sir.
I'm
Yes, sir,
getting
it is 1 plus.
Anyone got 1 plus?
Yes, sir.
Yes,
Yeah.
sir.
What's the roll number here?
The 19CH10002.
Second boy.
19CH 30034.
Anyone else got?
Yes, sir.
Tell what the expression you got, a plus b.
So I got a equal to peak minus b, so that is b to the power minus. So it's actually, so should I say like an entire expression?
Yeah, you tell the expression.
So peak minus, so a plus b is 1 plus e to the power minus 5 by tau into pi by omega by root over 1 minus pi square sine pi.
It's a very lengthy term you got. You substitute the omega
Yes,
value.
after substituting omega, I think it's 1 plus e to the power minus pi by 5 pi by root over 1 minus pi square into
Zeta
sine
is
pi.
not there?
Zeta, wait, zeta, okay, like I'm calling zeta pi. Yes, so like pi I mean zeta. E to
A
the power
sine.
minus sine,
Tell.
sine pi is equal to root over 1 minus zeta square. So that will cancel out. So peak minus 1, peak minus b, I'll get e to the power minus zeta into pi by root over 1 minus zeta square.
Correct. What's your number?
19CH10037.
Yes. Anyone else got?
Yes, sir.
What you got? A plus b, tell me.
1 plus exponential of minus pi zeta by root over 1 minus zeta square.
What's your number?
19CH30029.
Yes. So I think many of you got. Okay. So I hope that other students are trying. So this is the complete thing for overshoot, you see. Final expression I have written at the beginning. Now derivation we can do by considering yt by akp at t equal to tp. Tp we already determined. B we can determine from the final value theorem, that is yt by kp a at steady state condition, and in fact that is shown in the plot also equal to 1. Okay, considering this we get the first expression for overshoot a by b. Now if you have completed this, let us go to find the rise time. You first write the expression for rise time. I think if you revisit the plot, it's easy to understand the statement for ice time. It is the time required to reach first time the final steady state value. Okay. So how we can determine this rise time? Any clue, any answer from anyone? Based on this definition,
Sir,
can
putting y by kp equal to 1, we can find
yes. What's your roll number?
19ch30029.
Yes, correct. So rise time we can get by considering y divided by akp equal to 1. You just consider this in that expression and find the t value. I repeat, rise time corresponds to the final steady state value, that is nothing but 1. That means rise time we can determine by considering y divided by akp equal to 1. Fine. So you start with the given expression and consider there y divided by akp equal to 1 and rearrange to get the expression for small t. Carry on. Let's see what expression you are getting.
Sir, pi minus phi divided by omega.
Pi minus
Phi, the phase, initial phase.
pi minus phi.
That divided by omega.
Yes, sir, I'm
That
getting the same value.
divided by omega. Yeah, correct. What's your roll number?
So 30034.
Tanmoy, no?
Yes, sir.
Yes. Anyone else got the expression for t suffix r?
Yes, sir, same expression. Pi minus 5 divided by omega.
Yeah. What's your roll number?
19ch10047.
Sanskar Singh, no?
Yes, sir.
Yes. Anyone else?
Yes, sir.
Yes, sir, I'm also getting the same value.
Tell what value you got.
Pi minus phi by omega, whole divided by omega.
Yeah. What's your roll number?
19ch10007.
Adrija. Someone
Yes.
else also told?
Yes, sir.
Yes.
5 minus 5 upon omega.
Pi minus?
5 upon omega.
What's your roll number?
19ch30001.
Okay. So I think Abhishek Kumar, no?
Yes, sir.
Yeah. Many of you got this. So you just check the values, expressions. Is this fine? Yeah, it is exactly pi minus phi by omega. It is exactly pi minus phi divided by omega, or whole divided by omega. Next, you go to calculate this decay ratio. Next, we want to determine the expression for decay ratio. Again, you revisit the plot and see what is C, what is A. Both are indicated there. So decay ratio is basically the ratio of C to A. Next, we want to determine the expression for decay ratio. Now, decay ratio is basically C by A. C and A both are indicated in the plot. You revisit once again the plot and see what is C, what is A. Okay. Anyone can tell how we can determine this C or maybe B plus C? You revisit the plot. Based on that, I am asking the question. How we can determine B plus C?
Sir, B plus C will be value of response at time TP plus capital T.
Correct. What's your roll number?
30034.
Yes. So B plus C is basically YT divided by KP, AKP at capital T plus TP. You note down, then I think you can understand. B plus C is equal to, or you can put their equivalent sign, Y divided by AKP at TP plus capital T. I repeat, B plus C corresponds to the response Y divided by AKP. That response is Y divided by AKP. And we need to determine this response at TP plus capital T. B plus C corresponds to the response, that is Y by AKP, which you need to determine at TP plus capital T. Now check whether it is coming or not. Expression for A you already got.
So I'm not getting this value for c by a. I'm getting exponential of minus 3 pi zeta divided by under root 1 minus zeta square.
Tell again what you got. Exponential of
Minus 3 pi zeta divided by under root 1 minus zeta square.
This is what? After substituting 3t by tau 2?
This is the value for c by a. C value is 1 plus exponential minus 3 pi zeta divided by under root minus 1 by under root minus 1 by zeta square.
You tell me like this. What is the expression for b plus c?
The value for b plus c is 1 plus exponential minus 3 pi zeta divided by under root 1 minus zeta square.
Correct. What's your roll number?
19CH10047.
So we can determine easily C, no, because B is 1. And expression of A you already got. So C by A, I think it's matching.
Yes, sir. Yes, sir.
Yes. Anyone else got?
Yes, sir. Same value.
Tell me what is the expression for B plus C?
Sir, B plus C is 1 plus exponential of minus 3 phi zeta divided by under root 1 minus zeta square.
Yes. What's your roll number?
19CH30034.
Correct. Anyone else got?
Yes, sir.
Yes, sir.
Tell what is the expression you got for C?
C is, sir, exponential of minus 3 pi zeta by root over 1 minus zeta square.
Yes. What's your roll number?
30026.
Correct. Yeah, I think so. You understood how to determine this. Okay, this is a note how to determine. Let us come to the next topic, that is settling time or response time. Our next topic is settling time or response time. And we are using the notation TS for this. You note down the definition first. So as I mentioned, it should be certain prescribed band, or it is also called gap. Certain prescribed band, you may consider plus minus 1, 2, 3, 4, even 5%. So you are understanding for the same response, you will have different response time depending on this prescribed band. Okay. So for band limit of plus minus 1%, TS is 5 tau by zeta. But 2% like this. And this is just one sample derivation, how we can get it. One sample derivation I have shown here, how to get this. Let us consider the second case, Ts equal to 4 tau by zeta. So if you rearrange, we get minus zeta Ts by tau equal to minus 4. So exponential of minus zeta Ts by tau equal to, or it's equivalent to almost 2%. Okay. So any question based on this discussion? Student? Anyone has any doubt, question? If not, yeah, let us finish here. Okay, if you do not have any question, we will stop here. Any question? No. Okay, thank you to everyone then.
Thank you, sir.
Thank you to everyone.
Thank you.
Thank you, sir.